Hey guys, in this episode I'm going to address a question that I receive pretty frequently, which is how can I control feedback on stage? How can we prevent that from happening? You know, that terrible squealing sound that can come out of your sound system that often causes people to squeal. Well, I'd love to give you a simple answer and say all you need to do is purchase a feedback destroyer or a DBX drive rack with anti-feedback features, and that will automatically target and eliminate your feedback. I'd love to be able to tell you that all you need to do is to use a more feedback resistant microphone like the Audix OM7, which has an extremely tight pattern that will reject outside noise and prevent feedback. I'd love to tell you that there's a technique that you can use using an audio analyzer like SMART to identify the frequencies where the system will feed back and then just put in notches in your equalizer at those frequencies, be it a parametric or graphic EQ, and that will take care of your feedback issues. Those are all good tools, those are all good tips, but they're not the whole story, and they will not take care of any possible feedback issues. Feedback is simply a physical phenomena that happens when you have loop gain in a system and the inputs can hear the outputs. So let's take a quick look at what happens so we can understand the situation, and once we understand it we can make intelligent corrections to try to minimize the potential of problems happening. So, as I mentioned, all that's happening is you have an input into your sound system, your microphone, and that comes around into the electronics, which is a variable gain amplifier, and the output of that goes to a loudspeaker, which is, in my case, usually the stage monitor. I don't tend to have many feedback problems between the instruments or the microphones on stage and the mains, simply because the performers are typically behind the main speakers and a fair distance away from them. But the stage monitors, on the other hand, are right there on stage with the musicians, and they tend to be pointed at the microphones, creating a prime situation to generate feedback. And it doesn't matter what equipment you use or how good your sound guy is. If you have enough gain in the system and a loop where the inputs can hear the outputs, feedback can occur. And so we have a microphone that gets an input, the signal gets amplified by the amplifier and driven out the loudspeaker. And so when you speak into the microphone, you can hear it coming out of the speaker. So far, so good. Now, if this was all inside of a perfectly quiet room, how much gain could we turn up before the system started feeding back? Well, the system is not going to feed back in that situation because there's no signal going through the loop. It's a perfectly quiet environment. But as soon as we start speaking into the microphone, we've now have a catalyst to get this process rolling. So we speak into the microphone, sound comes out, and that comes back into the microphone a moment later. It takes a little bit of time because there's a distance between the loudspeaker and the microphone, and it takes time for sound to travel across the room. There is also probably a little bit of time delay imparted by your electronics, especially if they're digital electronics, but most of it will be due to distance. Sound moves at about 1,000 feet per second, so it moves pretty fast, but it does take a perceptible amount of time to move across the environment. This is why when you have a thunderstorm and you see a lightning strike, well, you see the lightning strike because light moves really fast, but then you hear the sound of the thunderclap a moment later. The thunder and the lightning happened at exactly the same time, but it takes a little more time for that sound to reach you. Okay, so we initiate the system by putting a sound into the microphone. That's the first loop, and we hear the output. The output then comes into the microphone, and let's just say the output is at a level of 1. Baseline. whatever it is. And that goes into the microphone, goes through the amplifier, and it comes back out again a second time. Now let's say the amplifier is turned down. It's not really all that loud. And so the second time that sound comes rolling through this loop, let's say it's only half as loud as the first time. So now it's at 0.5. I shouldn't say half as loud, I should say half as much power. And so the second time around the loop, it's a little quieter. The third time it comes around, it's going to be 0.25. The fourth time, 0.12, and so forth and so on. And so every time the sound comes through the speaker from the initial pulse, it gets quieter and quieter and quieter and quieter, and it just soon fizzles out. Will you hear this in the production? Yeah, you'll hear it. You oftentimes hear some splash coming off of the monitors into the vocals that are happening on stage, and that represents itself as somewhat of a bad reverb sound. Now, let's say on the other hand, our musician tells us, hey, I can't hear the stage monitors, I need more. And so you turn the gain up in the system so the stage monitors are louder. This loop now has more gain. Well, same scenario. As soon as the musician speaks into the microphone, that comes through the system, comes out the speakers, creates sound, which then goes back into the microphone, and we are at level 1. But that sound that came from the speakers into the microphone gets re-amplified and goes back out, and now because we've turned the gain up, let's say it comes out at level 2. That louder sound goes into the microphone, gets amplified even further, comes back around, and now it's at level 4. And so you can see it gets louder and louder and louder. And it will just continue to get louder until it reaches some kind of limit. And so we see that there's a threshold on our gain where if we're below that threshold, the system, as it goes through this loop, every time it gets quieter, quieter, quieter. But once we achieve that threshold or beyond, then it gets louder, louder, and louder. Now if it's getting quieter, well, the end result is it goes to silence and everybody's happy with that. But if we're above this gain threshold where every time the audio makes a loop, it gets louder, what's going to prevent us from getting any louder? Well, we have to reach the limits on something. So maybe in your signal chain, in your mixer, you've got a compressor or a limiter. Well, at a certain point that compressor or limiter may kick in and prevent the gain from being as much as it is, and that will stop the issue at a certain point. But if you don't have that, the thing that will stop the gain from happening is you've reached the top of the power amplifier. You just can't deliver anymore. So it'll drive the system right up to maximum power. And or the loudspeaker will fail because the loudspeaker is very likely not designed to handle all of the power all of the time from your power amplifier. And when the loudspeaker fails, it goes quiet, and that breaks the loop and cures the feedback issue. But that's an expensive cure, and it impacts the show, so that's not a good situation. So feedback can be dangerous to your loudspeakers because it can drive them into power territory that they're not designed to handle. So what can we do about this? Well, we have to reduce the loop gain somehow. So we turn down the amplifier and make sure that we stay below that stage of gain where we have a positive loop gain causing feedback. So it's all about stage volume really, which is we have to maintain rational stage volume to stay below the feedback threshold. Now, question is, what frequency is the system going to squeal at? We know that we can put in almost any kind of sound into the system. You could speak into the microphone with a baritone voice, and yet the system will quickly roll up into feedback and you get a high frequency squeal out of it. So what frequency is it going to feed back at is the question. Well, if we take a look at the frequency response of the audio system, and when I say the audio system, I mean all-encompassing, the whole shebang, your microphones, the loudspeakers, the physical room that you're in, the environment that everything is set up in. We might get a curve that looks something like this. Of course, your mileage may vary. Your curve will be different from this one. And this curve is very dynamic. It will change radically depending upon just exactly where you're taking the measurements. That is, if you were to observe the audio system in the middle of the audience, maybe you get this curve. If you observe it off to one side or the other side of the audience, or the very front or back, the curve will change. If you're on stage, you may see a different curve. If you move a microphone around on stage, well, you'll change the environment and that'll change. If the venue fills up with people, this will change. If the temperature or humidity comes in and makes a change, well, this will change. So it's a very dynamic situation, but there's probably some generalizations in this curve that will remain relatively consistent. If we look at the curve, what this is telling us is that the system has some places in its frequency response between the low frequencies and the high frequencies where its gain is not consistent. If it had consistent gain across the entire spectrum, this curve would be a flat line. But it's not a flat line because there are some irregularities in the system causing some shifts in gain. So that is to say that at this frequency and this frequency and this frequency, the system has positive gain. It's a little bit nonlinear. And so if I put in a pure signal source, these frequency areas, these tones will be exaggerated. And likewise, this one and right here will be artificially attenuated. So we don't have perfect reproduction in the system. And the question is, where is the system going to feed back? Well, it's going to feed back where the gain in the system crosses over that gain before feedback threshold. So if we have a threshold of gain before feedback that's sitting up here, and then we start turning up the audio system, the overall level, well, it's going to lift this entire curve upward. And who's going to hit that first? It's probably going to be this guy right here. So this is the frequency that the system is most likely going to feed back at first. And then if I continue to raise the gain of the system more and more, well, then we're going to hit this frequency right here next. And maybe down here. And so what can we do about this? Well, we can change the environment to smooth out this graph. And that might mean changing the room. It might mean using different microphones or with different polar patterns. It might mean moving speakers around, but most often how we address it is through equalization. And so what we will do is we will determine where these frequencies are at, and then we will put in a notch filter at those points in our equalizer to try to smooth out this curve so that we don't have those big peaks, and that way we can lift the entire curve higher before the system goes into instability. There's a number of ways we can do these notches here. One of them is to use a feedback destroyer device or a drive rack type device, which will determine this stuff somewhat automatically for us. We can put it into a learn mode and start turning up the gain, or it will turn up the gain until it detects feedback occurring. And when it does, when it sees that there's a particular tone in the audio spectrum that is much higher than the rest of it, it will then drop a notch filter in at those locations. And this is of course best done when the band is not playing, so that you can, during sound check, identify those areas where the system is most likely to go unstable and apply filters. Because when the band is playing, there might be a situation where maybe the band is quiet and you're doing a guitar solo and you hit a particular one note, and that one node is standing up tall above the rest of the spectrum, and the feedback destroyer device, being a dumb device, has a hard time determining the difference between an actual feedback squeal and a squeal from an electric guitar that you intend. And you don't want it dropping filters willy-nilly into your audio spectrum that are just stomping on the band and not controlling feedback. So those sorts of things are probably best done before the show. The other way that is commonly done is the manual approach, doing exactly the same thing with your equalizer, where you slowly turn up the gain of the system until feedback begins to occur, and you keep your hand on the control so that as feedback starts to occur, you back down a little bit so it doesn't let the system just completely run away and squeal. And then you can target those frequencies with your equalizer to stop the system from squealing at that frequency. For example, you turn up the system a little bit till you just hear the feedback, and then you think this is in the upper mid-range area somewhere, so you start going over to your graphic EQ, and one frequency band at a time, you just bring them down a little bit, and if the feedback stops, that's great. If the feedback isn't affected, well, you put that fader back to its zero position, and you try the next one until you target the exact frequency where the feedback is happening, and you apply a little bit of cut, maybe 3 dB, maybe 6 dB. And then you reiterate the process where now you turn the gain up a little bit more, and if that same tone starts squealing, well, you turn that fader on the EQ down just a little bit more. If a different tone squeals, well, then you target it on the equalizer and continue on. The alternative method of doing that is to turn up the gain in the system until feedback is just starting to present itself, and then you go to the equalizer and you go to each individual frequency band and you lift it up a few dB. And if you lift it up a few dB and nothing happens, great, put him back. If you lift it up a few dB and the system starts getting unstable and wants to squeal, well, then you put a little notch in at that point and set that fader down by, say, 3 dB. And you do this across the band, then you raise the gain up a little bit more, and you do it again. And you do this 3 or 4 times until you've found all those frequencies where the system is least stable. Now, as I mentioned, the system is going to want to feed back where there are irregularities in the response. And so you'll probably have a easier, smoother time of things if you use an audio system that has fewer irregularities in its response. Meaning that good gear tends to be more stable than inexpensive lower-end gear. And in addition to that, if you have a similar collection of stage monitors, they're all the same brand and model, and all of your microphones on stage tend to be the same, well, all of this equipment is going to share one particular response curve, which will be a whole lot easier for you to target and smooth out with any kind of electronic correction. If you have several different brands and types of stage monitors, and each musician has their own favorite mic and they're all different, well, each of those pieces of equipment are going to have their own individual response curves, and there is multi-way interaction between all of the different mics and all the different speakers, and it's going to be really hard for you to come up with unified curves for correction for that hodgepodge of gear. And so you'll probably have a little bit more of a difficult time controlling your stage feedback if you have a whole variety of different gear on stage, as opposed to if you can standardize on a particular kind of monitor and a particular kind of vocal mic. Now, as I mentioned here, the whole system is the result of the inputs hearing the outputs. And so we don't want our stage microphones to be hearing the speakers that are on stage. And we can do that through the use of directional microphones. So we keep the stage monitors or other sound sources on the back side of the microphone or off to the sides where the microphone is least sensitive. And being least sensitive, that means it's a reduction in gain overall. There have been some other techniques where people have used 2 microphones set next to each other and wired in reverse polarity. So the two microphones are wired together, one of them swings positive, one swings negative, and they cancel each other out. So any sounds in the vicinity tends to hit both microphones more or less equally, and it all gets canceled out. And then the musician just sings closely into one microphone away from the other one, because that makes a big difference between the two mics, and that's the only signal that comes through. So sometimes you'll see old shows, like from the late 60s or in the 70s, where there's two microphones on stage and the performer's singing into one of them, and that's what they're doing. We don't see too much of that anymore because, well, it didn't really work that well. But there is one thing that does work very well for controlling feedback on stage. Well, two things. One is just simply lower volume on stage. If you can turn the whole stage volume down, that means you don't need as much coming through the stage monitors, and you've reduced the gain, and you get the gain comfortably below the threshold of feedback. That works well. And lower stage volume almost always tends to be a catalyst for a better sounding show. You get less splash coming into the microphone, so you get clearer vocal signals. Everything sounds better. The other approach, which is related to that, is you get rid of the stage monitors. You have musicians use in-ear monitoring. And if you can do in-ear monitoring, well, you can dramatically reduce the stage volume, and you've reduced the opportunity for any amplified signal to come right back into the microphone. Now, there is an issue to be aware of, which is if you have some musicians on stage who are using in-ears and some musicians who are using stage wedges, in those cases you want to be especially careful to avoid feedback in the wedges, because if that does occur, the feedback will likely get coupled right into the bus that's driving the in-ear monitors, and having squealing feedback into your in-ear monitors is really uncomfortable, and so you probably won't make friends if you have a lot of feedback at your shows or people using in-ear monitors. But if the entire band is on in-ears and you don't have any sort of fold-back wedge monitors making sound, well, your opportunities for creating feedback have been radically diminished, and you'll probably have a better, cleaner sounding show for the audience. So I wish I could offer up a magic solution and say all you need to do is buy this piece of gear and you can take care of all of your feedback issues, but it just isn't that simple. But it's simple enough that it's just simply a matter of gain before feedback. So if you can reduce the gain, you can reduce your chances of getting feedback. And if the stage monitors aren't loud enough because you are forced to reduce the gain to that point, well, maybe you should try reducing other things on stage so that you can hear the monitors. I hope this was interesting and useful information for you, and I hope that you choose to come back and watch some more. I would appreciate it if you'd take a moment and hit that subscribe button if you haven't already, and hit the bell notification icon so when new content drops, you're informed and you don't miss anything good. Thanks again for tuning in to this episode of Sound Advice, and I look forward to seeing you again soon on the next one.